All right, so we're back here continuing to talk about constrained diffusion. This is the fourth video in a series of videos looking at this idea, and again, diffusion being movement of mass from high concentrations to low concentrations based on random molecular motion, and this is analogous to heat transfer. And we're looking specifically at this problem where we have two infinite sinks that mass is going to move into from some initial concentration here in the middle, and there's some initial concentration across this interval of 0 to L. Here at the beginning, there's a concentration profile, and we're going to call that f of x. And we're going to look at the case where f of x is just a constant value of c0 there. And so we said that we're looking for a function that will have this kind of behavior here, where it starts at this high level, drops down to 0 on the sides, and then as mass moves out, it goes down to 0. We said that this is governed by Fick's laws, and specifically Fick's second law, and we came up with a solution for that in the next video here. So starting with Fick's law and coming down and saying this is the general solution. It has to have this sum of a sine and a cosine term times an exponential. And then we looked at the boundary conditions in the last video, and we said that, so starting from those boundary conditions, that the solution would need to look something like this. And so this is our general solution, and it turns out that there's going to be an infinite number of terms in that solution that are all going to have a form of a sine and an exponential multiplied together, and we need to find the coefficient here to make this satisfy the initial condition. So in this video, I want to look at how we can find the initial condition, which remember was that arbitrary function f of x, but we will solve it specifically for the case here of f of x is c0, which is a constant. So our initial condition c at t is 0 is got to be, so again, if I put in t equals 0 here, then I get sum from n equals 1 to infinity of a sub n times sine of n pi x over L, and then the exponential term went away, and that needs to be equal to our initial function f of x across that interval, which in this case we're looking specifically at c0. I'm just going to leave it as f of x as long as I can, because we can work with the result later for a different kind of initial condition. And we said that this is called a Fourier series, and it's a very useful technique that was discovered by Fourier. Across any finite interval, you can write it as a sum of sines or cosines to approximate that function using this sum, or it's exactly equal to the value of that function if you take an infinite number of terms. Of course, we can't do that in reality. But so let's see now, we need to figure out what the terms are that are in front of each of these sine terms. So n is 1, we get a sine of pi x over L, and there's some term in front of that. And then the second term would be sine of 2 pi x over L, some number in front of that, et cetera, et cetera. And we need the formula for the n, if you will, to make this work. And so the trick that we're going to use to figure out the value of n, so find a sub n using a basis function. Okay, again, you can go look more about these ideas in other places, other references, I'm sure. I can maybe post some links later. So we're going to use a basis function here, which we're going to call phi, and that's going to be, in this case, we're going to choose phi as m pi x over L, and then we're going to integrate it over our interval here, x equals 0 to x equals L. Okay, so we're going to multiply both sides of this equation by that, and we're going to integrate it from 0 to L. And again, I can do whatever I want as long as I don't break any rules. And it turns out that this is going to help us figure out what a sub n needs to be. Okay, so making that substitution, we have integral from 0 to L of sine of m So m is some other number here, pi x over L times the summation from n equals 1 to infinity of a sub n sine of n pi x over L dx. So multiply that, and then I need to do the same thing on both sides. So integral from 0 to infinity of f of x sine of m pi x over L dx. Okay, and so this is really the key integral that we have to perform, but this part on the left side doesn't depend on the initial conditions. So let's simplify this first a little bit. And so here we have an integral and we have a sum. And so we can't, so we can move this inside and outside the sum if it doesn't have an n in it, which it doesn't. Okay, and a sub n is a constant, remember. So if we do that, we can then rewrite this left side as, see if I can get this right. Yeah. Oh, sorry, before, so we need to, so those are things we need to keep in mind. The other thing that we need to keep in mind here is that we're integrating a sine of m pi x over L and sine of n pi x over L. So let's just think specifically about that. And integral from 0 to L of sine of m pi x over L times sine of n pi x over L dx is equal to 0 if m is not equal to n. Okay, and this is because these two functions are called orthogonal. And again, you can go and look up more about this, but so this means that they're orthogonal. This is a word that's used. Orthogonal functions across the interval of 0 to L. Okay, and again, you can go look at that. But so if m is equal to n, so really this makes life a lot easier because, see, we have an infinite number of terms here that we would need to go and do this integral on because there's an infinite sum, but really all the terms in this sum are going to go away when I do this integral here because this is 0 unless they're equal. In the case they are equal, then I can just replace the m with an n, and then I am left with integral from 0 to L of sine of n pi x over L quantity squared dx. Okay, and yeah, again, this needs to be still on the left-hand side equal to that other integral. And I'm just going to switch the m back to an n because it doesn't really matter. Because we're not dealing with that side right now. Okay, so now what we said is, yeah, our infinite sum here got replaced with this, and this is times a sub n again, so there would have been an infinite number of them, but I can just pull that outside because it's a constant. And so this integral here on the left side, this is a sine squared. If you do a trig identity, I'm not going to go through like all the steps of the trig identity and integral algebra. Okay, you have to do like integrate by parts, and we get that this integral here, sine of n pi x over L sine squared, this actually is equal to just L over 2 if you go through and do this. Okay, I'm not going to show these steps again because this isn't really anything that should be new. It's just a matter of doing some trig and some calculus that you can go look at other videos if you need to go do this on your own. All right, so we get that then this whole thing becomes just L over 2, and that then tells us that a sub n, we can now solve for it. A sub n has to be equal to 2 over L times the integral of 0 to L of f of x times sine of n pi x over L dx. Okay, so this means that we can now find all we need to do is perform this integral for whatever our initial function is, f of x, and we can find all the coefficients that we need for our equation up here to satisfy the initial condition. And so let's look at, as an example, the case of, so f of x we said is equal to c0. This is the easiest one, but as long as you can figure out how to do this integral for whatever function you put in there, you can then satisfy the initial conditions and then have a summation term here that you can approximate in a computer later. Okay, so if f of x is equal to c0, then we have a sub n needs to be equal to 2 over L times the integral from 0 to L of c0 times sine of n pi x over L dx. And so the c0 is a constant, so that I can pull that out. 2 times c0 over L, and then looking at doing this integral, so sine becomes cosine and cosine becomes negative sine. So I need a negative cosine in order to make this work, and then I've got to remember the chain rule, so n pi over L. So I need to multiply by L over n pi and then times a negative cosine. That should give me this function if I were to take its derivative. So I can write that as negative L over n pi times cosine of n pi x over L. And I need to evaluate that across the interval of 0 to L. Okay, so this should have a derivative of that, and I pulled the C0 out. And these two are constants, so they can, or these terms here are all constants, so they can come out because they'll be in each term. And then we're left with a sub n equals to 2c0 over, and so looking at the L's, those are going to go away. 2c0 over n pi times, so again, pulling that out. And so if I put in an L there, I get cosine of n, or a negative cosine of n pi. And if I put in minus 0, so it'll be minus a negative, so that becomes positive. So this should just be 1 minus cosine of n pi. Okay, so the second term is a 1, and the first term is a negative cosine of n pi, and I just flipped them around. And okay, so now we need to figure out what this is. So remember that n is an integer, and so it's some integer multiple of pi. So if n is 0, remember our unit circle, the cosine is on the unit circle where we're at, and so we're starting at 0. That has a cosine of 1, and then if you go over the other side of the unit circle, you're at pi, and that has a cosine of negative 1. If you go to 2 pi, then you're back at 0. And so really, if n is an even number, we're going to get cosine is 1, and if n is an odd number, then we're going to get a negative 1. Okay, so let's look at that. So let's say if n is odd, then cosine of n pi is equal to negative 1, and 1 minus cosine of n pi is just equal to a 2. Okay, so if that's a negative 1, the whole thing becomes a 2. On the other hand, if n is even, cosine of n pi is equal to positive 1, and 1 minus cosine of n pi is equal to 0. So really what this is telling us is that this whole thing, our a sub n coefficient for the even numbers is 0, so it can be ignored. And then if it's an odd, then we need this to be a 2, or a sub n is equal to 4c0 over n pi for the odd numbers, and then 0 otherwise. And so I can do a little trick here. So we'll reindex, we'll call it reindex with n is equal to 2m plus 1. And if I do this with m equals 0, 1, 2, ... So if m is equal to 0 here, then I get n is equal to 1, and that's one of my odd terms. If I do m is equal to 1, then I get n is equal to 3. That's one of my odd terms. So if I do this little reindexing trick here, I can make my summation from 0, 1, 2, 3 instead of 1, 3, 5 with n. Okay, so by simply replacing the n with a 2m plus 1, now I know that my terms here, all my a sub n terms, are going to be 4 times c0 over 2m plus 1. Okay, so changing it to a sub m, I guess. And I can then go back and put them into my original equation, and I get my solution here. So c of xt then has to be equal to the summation from m is 1 to infinity of 4c0 over 2m plus 1 times pi, and then times sine of 2m plus 1. I guess I should write up here that we're going to reindex, and then we get a sub n is just equal to 4c0 over n pi. And or if I replace the n with a 2m plus 1, that's this term, and then we have sine of 2m plus 1 times pi x over L. Okay, that's the sine term. Maybe I'll put it in brackets to make that a little bit clearer. And then I'll write for the exponential term here, I'm going to write it as exp, and that's going to be a negative 2m plus 1 squared times pi squared. Again, this is all from up here. And I'm going to write it as dt over L squared to kind of separate it from the other parts here. So dt over L squared. And so now we have finally a solution that satisfies our governing equation. It needs to have those, we said there are any number of sine and cosine combinations, sine plus a cosine times exponential. And then it satisfies the boundary conditions because this whole thing will go to 0 at x equals 0, and then at x equals L, each of these terms will then add up to 0. Okay, and then at t is equal to 0, we can add them all up and approximate our initial function. So here we have a complete analytical, quote unquote, solution here, or exact solution to our differential equation. And so a lot of times in a math type class, you might just stop here and say, we're done, we have the solution. Of course, working with this equation is still difficult because it's an infinite sum and it's got these big messy terms. So I will look next at how we can actually implement this in a way that we can work with. And I would also note here that most of the work was done before we actually got to the initial conditions, and so you can go and look at a different initial condition here. Instead of using C0, you could replace this with like, x over L, let's say, on the interval, and then all you have to be able to do is figure out how to do this integral, and you can come up with your value for your coefficients here, which, again, in this case, it turned out to 4z0 over n pi, and then we replaced n with 2m plus 1. But you can do this for other functions. And this is handy for looking at other initial conditions, but you can actually also use it to deal with boundary conditions. So I'll make another video where I look at how you can use a slight modification of this one to deal with different boundary conditions also. Okay.